Hello everyone. Okay, so let's begin. Let me share my iPad. Just give me 1 second. Okay. Okay, so let's begin. Let's just do a very quick recap of like where we left in the previous lecture. So we started discussing about neural networks, and specifically like we were looking at how to train neural networks, or like how to learn the parameters W's and B's in a neural network, right? Like so, and we started discussing how to do backpropagation, and we just looked at the base cases and then we stopped there. So just to give a quick recap of like what we have seen so far, like here is a simple neural network where you first compute a hidden state H, which is G of W1x plus B1. Then you have the output Y, which is O of W2H plus B2, right? And you have a bunch of examples, right? Like, so let's say you have P examples. Now this is your error function. So the first thing that we did to do gradient descent is to actually create this huge computation graph, which also encompasses the error function, right? Like, so now in this case, this is just for an ith example, right? You have the output. Let me just put a highlighter. So you have the output y1 to ym, right? So then for each unit, you compute the error function, right? So then you add them to get the final E, right? So now this network takes an input X, it produces the output Y, and then it computes the error, and it is just giving you the final error E, right? So now using this network, you can actually compute dou E by dou X by just running this network backward using the procedure that we have seen in the previous lecture. Now, if you have a data set of P examples, then you could replicate this network P times, and you collect all the errors from these P, and you extend the network further to get a single scalar E, right? So the whole idea here is like you take your network, you extend the network with all the error functions that you want. So finally, the loss is a unit in the graph itself. Now, how do we do how do we compute gradient with respect to parameters in this graph? So we started looking at a bunch of base functions, right? Like, so to before we go to the base functions, like, so we looked at the idea of using B diagrams where every unit is going to store the computation F, but it will also store the F dash, corresponding F dash, right? Like, so now, for example, let's go to the base case. Yeah, so now this is the first base case, which is function composition, right? So maybe let's do the base cases once again to begin with. Okay, let's go to today's lecture. So now we want to do backprop, and there are three base cases. Case one is function composition. So in this case, I have y is equal to f of g of x. Okay, now this is represented as you take the x, you pass it through the G unit, which also has the corresponding G dash. Then you pass it through the F unit, which also has the corresponding F dash, right? Now, if you run this network forward, you get G of X, and then you get F of G of X. Now, let's see how to run this network backward. If you want to run this network backwards, right? So you will put a 1 here. You'll multiply 1 with F dash, so it becomes F dash of the input, right? So then you multiply F dash. So this is F dash of G of X, okay? Then you multiply this with the G dash here. So finally you get G dash of X multiplied by F dash of G of X, okay? Now this is exactly the derivative of this function y with respect to x, right? This is exactly dy by dx, right? Now, similarly, the second case is function addition. Now, let's say I have a function y, which is f1 of x plus f2 of x. Okay. Now, how do I represent this as a computation graph? So I take the x, I pass it to f1 function as well as to f2 function. Okay, f1 is going to maintain f1 dash of x, f2 is going to maintain f2 dash of x. Then you add these two things, and we have seen that if you're adding the derivative with respect to one of them is given by 1, right? So then finally, you get f1 of x plus f2 of x. If you run this forward, you get f1 of x plus f2 of x. Now let's see how to run this backwards. So if you do if you run this network backwards, you start with 1, okay? Then the 1 multiplied by this one is this, the 1 multiplied by this one is this, right? Now you multiply 1 with f1 dash of x. You multiply this one with f2 dash of x. Now, whenever you have this connectors, like you just add it. So this becomes f1 dash of x plus f2 dash of x, which is exactly dy by dx, right? So finally, we have case 3. Okay, so case 3 was weighted, the idea of weighted edges. So what if I have a weight? Okay, so now this is y is equal to wx. Now in this case, the idea is I just have this edge which has a weight w. Okay, if I pass x to it, it's going to give me wx. All right. Now how do I run this backward? If I want to run this backward, I just multiply the 1 with whatever the weight is. So the output is w. Okay, now this w is exactly dy by dx. Is that clear? Okay, so now I'm going to claim that by using these 3 basic operations, function composition, function addition, and weighted edge, you can implement a neural network using this computational graph way, right? So I will let you think for 30 seconds. Like what I say here is like by just using these 3 operations, composition, addition, and weighted edge, we can actually implement any neural network that we want, right? Like, so just to give you an example, if you have h is equal to f of wx plus b, okay? Now this wx can be implemented with weighted addition, okay? Then you have another addition function here. So then you have the function f, which is the composition of the input, okay? So you could represent this by using these 3 basic modules that we have, okay? So now we are going to use these basic modules to implement our backpropagation algorithm, okay? So now the idea is very simple. Like first stage is feed forward stage. In the case of feed forward stage, you take the input x, you feed it to the network, okay? And in each node, you will compute both. In each node f, you will compute both f, the function itself, and also f dash. Okay, and you're going to store both f and f dash. Okay, so now in the backprop stage, you're going to run the network backward. How? You're going to feed a constant 1 in the right side of the network. Okay, and then like every incoming information is added, like basically like you integrate the information throughout, right? And like whatever output that you get in the left side, right? So that is basically the derivative of the function with respect to input x. Fine. So remember that what we actually care about is not dy by dx. Can someone tell me what we actually care about? We don't care about dy by dx. So what do we care about? What's the gradient that we are interested in? Yeah, so right. So we care about dy by dw, right? So we can easily get dy by dw from dy by dx. Okay, so we are going to see how to do this, okay, later. But for now, I want to, we normally don't do proofs in this course. As an exception, I actually want to prove that this backpropagation algorithm will indeed compute the correct gradients all the time. Okay, because this is one of the central algorithms that we will use often, and we want to make sure that this algorithm is like, it has a guarantee that it is going to compute the gradients correctly. Okay, so now the proposition here is the backprop algorithm computes the derivative of the network function f with respect to input x correctly. Okay, this is important because like the way in which I explain this algorithm, it is a general algorithm, right? Like it is not dependent on any architecture that we have. Like, so you could have any type of neural network architecture, any type of network, and the backprop algorithm is going to compute the gradients correctly. Okay, so how are we going to prove this? So we are going to prove this by induction. Okay, I'm just going to give you a very hand-wavy proof. You can have the detail, you can find the detailed proof in the lecture notes. Okay, so we're going to do proof by induction. So for people who already know how to do proof by inductions, like we need a base case, right? Like we have already, that's why we saw 3 base cases, right? Like, so there are 3 base cases: units in series, something like this, FG, right? Then we need units in parallel, which is what the FG function was. Then you have weighted edges. So we have already proved this before. We have already proved by pictures that the derivatives that you would compute for units in series, parallel, and weighted edges is correct. Okay. So now my induction hypothesis is, I'm going to assume that the algorithm actually works for any feed-forward architecture, okay, with n or fewer nodes. Okay, now the classic induction step is, if the algorithm works for n nodes, n node network, okay, then it will also work for n plus 1 node network. Okay, now I just need to prove this statement. So if I can prove that if this algorithm works for n node network, it will also work for n plus 1 node network, then we are done, right? Like, so then you can have any type of network architecture and this algorithm will find you the correct gradient. So how am I going to do that? So to do this induction, we are going to consider an arbitrary neural network. Okay, so let's say I have some input x, and this input goes to a network. We don't care what the network is, okay? And let's say that at some point, this network is producing a bunch of functions, f1 of x, f2 of x, to fm of x. Okay, now these functions are integrated to the final output. Okay, so we have some nonlinear function phi. Okay, so phi of s, phi dash of s. There is a weight to integrate these things, and final output is f of x. Okay, now this network is basically f of x is equal to phi of w1 time f1 of x plus w2 times f2 of x plus wm times fm of x. So this is a neural network, okay? And this neural network has n nodes. sorry, n plus 1 nodes. Okay, now consider these individual nodes f1, f2, f3, sorry, fn. Okay, maybe let's just take f1 of x. Okay, now how many nodes, what can you say about the number of nodes in a network which starts from x and ends at f1 of x? So I'm saying that the total network has n plus 1 nodes. Now the question is, what can you say about the number of nodes in the network starting from x to f1 of x? Any answers in chat? By nodes, I just mean the, okay, by node, I just mean the units, not the layers. Okay, so okay, so the question is, so the total number of nodes in this entire network is n plus 1. Okay, now how many nodes, like, or what can you say about the number of nodes in the network which starts from x and ends at f1 of x? So I think Olson's answer is correct, and I think some of you are answering correctly. So see, one thing I know for sure is there's an extra node here, right? So there has to be only less than n plus 1 nodes, which ends with f1 of x, right? So if I launch my back propagation procedure by putting a 1 here all the way to x, I will get f1 dash of x. And that will be the correct f1 dash of x, right? Like, I don't know what is inside this black box, but since it has less than n plus 1 nodes, since it has at max n nodes, we already made an assumption that if there are n nodes, backpropagation works. So I can easily find f1 dash of x. Similarly, the same argument goes for f2 dash of x. I can easily find f2 dash of x. I can correctly find fm dash of x, right? Now, what is the actual f dash of x? So the actual f dash of x is phi dash of s. S is the whole thing, okay? This is the whole thing is s. Phi dash of s multiplied by, multiplied by, you differentiate inside. When you differentiate inside, you get w1 times f1 dash of x plus w2 times f2 dash of x to wm times fm dash of x. This is what the output should be, right? Now, how can I get this output? Like, all I have to do here is put a 1 here, multiply this 1 with this phi dash of x, okay? So that when it passes through w1, it becomes w1 times phi dash of s, right? When I pass through this, it becomes w2 times phi dash of s. When I pass through this, it becomes w3 times phi dash of s. Then you multiply that with f1 dash of x, f2 dash of x, fm dash of x, you get the same thing, right? Like, so now this is exactly what backprop would do too. So what would backprop do? It will always put a 1 here, multiply things if it comes inside the node, and multiply by the weight if it passes the node, right? So whatever procedure that I have done here to get this f1 dash of x is exactly what backprop will also do, okay? Okay, so now this is a very like hand wavy explanation of the thing. Like, it could be more, it is more precise in the lecture notes, but is there any questions here? Do you get the gist of the proof? Like, so what I have done here is, like, I assume that Backprop works for n nodes, and I proved that going from n to n plus 1th node can be exactly done using the Backprop procedure. Any questions?
No questions in the chat.
Okay. Okay, so now that we have seen an algorithm to compute dou y by dou x, okay, Now let's see how to move from dou y by dou x to dou y by dou w, which is what we care about. Okay, so how to do learning? To do learning, we need to do gradient descent. To do gradient descent, you need dy by dx, right? So learning with backprop. Okay, so now consider some weight wij. Okay, so now this wij weight is connecting ith node to jth node. Okay, now this weight wij can be considered as input channel into the subnetwork made of all paths starting at wij and ending in the single output of the network. Okay, so I have node I, node j, then there is a output, final output, let's just call it y. Okay, now we call the final output as E, right? So let's just have the final output, which is the error. Okay, now I have this connection wij. Okay, so then it goes through a bunch of things to the error. Okay, now you can consider this wij as input to this whole network, right? Now, what is actually fed into this network is whatever the output of this ith unit, let's just call it OI. Okay, so you multiply OI with wij and pass it through this network. So when you do backprop, when you stop at this point, your backprop, you will get dou E by dou OI wij. Is that clear? So let's consider x to be OI wij. Okay. Now if I pass this x inside this network, then I can compute dou E by dou wij as dou E by dou x by dou wij. So dou E by dou x is exactly dou E by dou OI wij, and dou x by dou wij is OI, right? So now whenever I want the gradient with respect to this, all I have to do is multiply the gradient that is coming from the right side with the output of the previous unit. Okay, now this basically means that each node I should store the output OI of the node in the feed forward step. Okay. Also, it should also store the cumulative result of the backward computation up to that point. Up to that node. Okay, so we are going to call that as del. So whatever value of backpropagation I get here, let's just call that as del. Okay, so now dou E by dou wij simply becomes OI multiplied by del j. Okay, now if you want to do gradient descent, you can easily do del wij is equal to minus gamma times OI del j, and wij is equal to wij plus the gradient. Okay, or you could also write this as the usual form, which is wij is equal to wij minus gamma times the gradient, which is OI del j. Is that clear? Okay, so now so far we discussed about neural networks and backpropagation in a much more general way, right? Like, so it could be any type of network, right? Like, but in practice, we normally use layered networks. Well, the idea is like, let's say I have n input units, then k hidden units, and m output units. Okay, so now I would have a network like this. In this case, I have n input units, k hidden units, and m output units. And you can see that I add a 1 here, which is extending the input for the bias. So once you add the 1, then this W1 is also going to encompass the bias. Okay, so maybe this is wrong. It should be, as per our notation, it should be W1, W2. Okay, so now what is W1? W1 is actually n plus 1 cross k matrix. Similarly, W2, let's just put a bar so to mention that it's extended with the bias, is k plus 1 cross m matrix. Is that clear? Okay, so now how do I do backprop in this one, right? Like, so now let's consider an n-dimensional input vector. Okay, I'm going to call that as O. Okay, now we can actually extend this as O hat, which is basically O1 to On with an additional 1. Okay, now the pre-activation is given as, for the first layer is given as, let's say sum net j is equal to summation over I is equal to 1 to n plus 1 wij of 1 oi hat, right? Now then the activation is given by oj of 1 is equal to s of some activation function summation over I is equal to 1 to n plus 1 wi, it's exactly the pre-activation. Okay, so now I can actually write this in matrix notation. Okay, so I would get O1 vector as S of O hat multiplied by W2, sorry, W1 bar. Okay, similarly, I could also write the next layer, the output. So this is the hidden layer. Okay, similarly, I could also write the output layer as O2 is equal to S of O11. Okay. Okay, sorry, you don't need the one here. O1, which is the hidden layer, multiplied by W2 bar. And you can generalize this to as many layers as you want. Okay, so now let's see how to do backprop for this specific architecture. Okay, so as usual, okay, so steps, let's go through the steps of the algorithm one by one.
There is some doubt in the previous page, Sarath.
Yeah.
Why there is 1 in the input vector?
Okay, so the one is to, like, remember that, like, if you normally write your equation, it is going to be W1x plus bias, right? Now, instead of writing like this, I could just write it as W1 extended x, what is the notation I use? X hat, right? So basically I just add a 1 here so that the bias goes inside, so that the whole thing becomes one matrix vector operation. Okay. Okay, so now the first step is to actually compute the extended network, right? Like, so you can see the extended network here. So basically, like, this is the ith hidden unit. From the ith hidden unit, you have a bunch of output units. Okay, so there are m output units, and for each output unit, you compute the error function. Now this is squared error. For every squared error, like, you also have the corresponding differentiation term here, right? And you finally sum all these squared error to get the error. Is that clear? Now, when you do feed forward, Step 1 is feed forward. Okay, so when you do feed forward, you give the input, you go through the network in like from left to right, you will get the error. Okay, now once you have the error, we are going to start the backprop stage. So the first step in backprop is to compute dou E by dou Wij of 2. So we have two layers of weights, right? Like, so first we need to compute the gradient with respect to the topmost or the rightmost layer of the network, which is W2, right? So once you have this, then you will compute dou E by dou Wij1. Okay, so now how to compute dou E by dou Wij2, right? To do that, we are going to consider this subpart, like where I have the ith hidden unit, and Wij is connecting this ith hidden unit to the jth output unit. Okay, so then for this jth output unit, you have the error function, then you finally sum it, right? So now all you have to do is to put a 1 in the end, and you go from right to left. Okay, so you put a 1 here, or you multiply 1 by 1, you get 1, right? Now you have this 1, you multiply this with whatever value is here, so you get oj2 minus tj. Okay, so then you multiply this with this term. Okay, so then you would get this term, right? Now that is the cumulative gradient. So del j of 2 is given by oj of 2, 1 minus oj of 2. So it's oj into 1 minus oj. Okay, can someone tell me what is the activation function that I'm using in the jth output unit if the differentiation is O into 1 minus O? Sigmoid, is that correct? Is everyone sure that it is sigmoid? Yeah, so it is sigmoid, right? So that's why I put O into 1 minus O here. Okay, so the integrated gradient is given by this, right? Now, if I want dou E by dou Wij of 2, all I have to do is multiply this integrated gradient with the input to this weight. The input to this weight is OI1. Okay, then finally, the last step is we are interested in computing dou E by dou Wij of 1. Okay, so now what is the gradient with respect to Wij of 1? So to do that, like we are going to consider this hidden unit J. Okay, and this OI is the input unit. So input to hidden unit. Then from this hidden unit, you have a bunch of output units, right? So now these are connections to the output units. Okay, now these output units actually get these backpropagated errors, del 1, 2, del 2, 2, and so on, right? Now, all you have to do is to go backward. So when you go backward, you multiply these two things together, you multiply these two things together, you multiply these two things together. Now, since they're coming to one place, you add them. Okay, so that is what this is doing. And then you multiply that with this value. Okay, now this is my del j of 1. Okay, now I can easily compute dou E by dou Wij of 1, which is simply del j of 1 multiplied by the input to the W weight, which is OI. Okay, so now once you compute these things, the final step is to do weight updates, where the idea is, maybe I'll just write it as the normal equation. So Wij of 2 is given by Wij of 2 minus gamma times OI1 del J2. Okay, similarly, Wij of 1 is given by Wij of 1 minus gamma times OI del J of 1. You will do this for all the weights in the first layer and the second layer. Okay, so far our discussion was just based on one example, right? Like, what if we have more than one training example? So when you have more than one training example, like you would compute the gradient for wij of 1 with the first with respect to first example, you'll compute it with respect to the second example, you'll compute it with respect to the pth example, right? So then the final gradient del wij of 1 is given by the sum of all these things, del 1 plus del 2 plus del p. Okay, now so now this is a small quiz. Let's say I have p examples. Okay, if I consider all the examples, like I add the gradient with respect to all the examples, and then I make my gradient update step. So what type of gradient descent is this? Christoph, to answer your question, yeah, O1 with a superscript is just the input of the network. O1 with the superscript 1 is like the value in the hidden layer. To give you some, okay, so maybe this notation is bad. I'll try to fix it for the future. O is the input. O1 is the H. O2 is the Y. Okay, so if I use all these gradients, if I sum all these gradient and then do a gradient update, what is it? So if I sum all example gradients, yeah, it's not stochastic. Okay, it's not stochastic. So this is full batch gradient descent, right? Or I could also consider only one example for single update, which is the stochastic gradient descent setting, right? Or I could consider a mini batch of examples. And that becomes mini batch gradient descent. Mini batch stochastic gradient descent. Is that clear? Okay, so now this algorithm can be efficiently implemented, like when you're actually implementing it for yourself. Okay, so you can actually take all these for loops over every possible weights and so on, and represent this whole algorithm in a concise equation as matrix form. Okay, so now we're going to look at backprop in matrix form. It's very simple. Like all you have to consider is like, let's assume that all the derivatives are stored in matrices. Okay, so now D2, which is the derivative in the second output, is O12 times 1 minus O12, right? So we are going to consider this to be in a matrix 1 minus O22, OM2, 1 minus OM2. Let's just call this as D2 matrix. Okay, the rest of it's a diagonal matrix. Okay, similarly, the derivative in the first layer, O1 into 1 minus O1, right? So that is given as O1 into 1 minus O1, O1 into 1 minus O1, okay, until OK into 1 minus OK. Okay, I will definitely change this O notation next time. So this is all 0. Okay, now similarly, I could write the derivative with respect to the error function as a vector minus t1, O22 minus t2 to OM2 minus tm. Okay, so now del 2 can be efficiently represented as just d2 times e, matrix multiplied by the vector. Okay, I will leave it to you to go back and verify that this is exactly the same as what we implemented before. Similarly, del 1 can be represented as d1 multiplied by w multiplied by del 2. Okay, so now the gradient with respect to W2 is given by minus gamma times del2 O1 vector. Similarly, the gradient with respect to W1 is given by minus gamma time del1 respect to O, with respect to the input O. Okay. Now you can see that the entire gradient is computed by using either vector matrix operation or matrix vector operation or vector vector multiplication. Like it is just one of these three multiplications, right? So now this kind of vector matrix multiplications can be efficiently done in GPUs. So often when you train neural networks, they're going to be slow in CPUs, but you can parallelize them in GPUs by exploiting the fact that all the operations here are matrix operations. Okay. Now, in fact, it is actually very easy to generalize these gradients to any number of layers. Okay. So let's say you have a L layer network. Okay. Then the del L, the final layer is given by del LE. Del I in any layer I is given by di wi plus 1 del I plus 1. Okay. Or I could just expand this. Del I is given by di wi plus 1 all the way to wl minus 1 dl minus 1 wl dle. I could just expand the whole thing. So you could generalize this equation to any number of layers as you want. Okay. Okay, I think that concludes our discussion on backpropagation. So any questions? Lowercase e is the error. Yes, that's right. But I think instead of starting a new topic, like I would stop here. So I will take questions. Any questions? Is it same if your network has loops? That's a good question. If your network has loops, the backpropagation algorithm will still work. But how to do that is something that we will probably learn in a couple of lectures. Next week, for sure. Any other questions? Okay, so the number of nodes in the hidden layers is always greater than the number of input nodes. It need not be the case. You could have any number of units in the hidden layer. And I guess it also depends on the problem, right? So like if you have like a huge input vector, then probably you would reduce it to like a smaller number of units in the hidden space. So the number of units in a hidden layer is a hyperparameter. Yeah. So just to remind you of the hyperparameters that we have in neural networks. Okay, can people list what are the hyperparameters that we have in a neural network? Okay, as we have already said, the number of layers, number of units per layer. Anything else? Activation functions. Anything else? Yeah, the dimensions is what I mean by the number of units per layer. What do you mean by the configurations of the layers? Okay. Uh, yeah, well, yeah, so you could say network. Okay, let's just call that as network configuration. So far, we are only discussing fully connected layer-wise connected networks, but you could have any type of fancy network connection as you want. Yeah, learning rate for sure is gradient descent, right? Loss function. Okay, what else? Batch size. Okay, good. So what else? Number of epochs to train. Okay, so I'll probably put the last function up because these are all gradient descent hyperparameters, right? What else? I think we have covered pretty much all the hyperparameters that you can think of. So it's actually, okay, the reason why we do this exercise is like it's actually very important to know what are the hyperparameters for your model so that you can tune these hyperparameters efficiently, right? Like, so it's not just enough what are the to know what are the hyperparameters. So you should also have some working knowledge of what would be the impact of changing each of these hyperparameters. And that only comes by practice, right? Like, so you need to try a lot of things to get a practical knowledge. What is the parameter after the number of layers? Number of units per layer. So it's the dimension of the layer. Yeah, that's a good point. So how do you initialize the weight? That is a subtle hyperparameter. So weight initialization. That's something I think we did not talk about, and also something that we will probably not talk about in this course. So you could initialize your weight with small negative value, like sorry, small random values. Okay, maybe this is an interesting question. Probably I'll keep that question for the exam. I'm not going to ask it now. No, I was about to ask a question now, Masud. I decided not to ask it now and keep it for the exam. Okay, so if there are no more questions, I will stop here. So I think there was a question about final exam. Okay, so just give me one more week to tell you all the details about the final exam. So I'm still figuring out. I see that almost all the courses are doing it physically at Poly. Like I decided not to do that so that it's convenient for you guys. But give me like one more week. By next week, I'll definitely tell you the exact format in which we are going to do this online exam. But the exam is going to be online during the time allotted for the course by the university. I think it is December 19th, 9:30 in the morning. Correct me if I'm wrong. Okay. Oh, also another important reminder, as you guys might have received the email, like I extended the deadline for creating your teams to tomorrow, but try to do it by tomorrow. So I think currently we have 33 teams, which is 99. Like there are still like I think 7 or 8 teams which hasn't registered yet. So try to do that. And most importantly, there is a tutorial tomorrow on more advanced PyTorch functionalities, which I think will be very useful for you for your competition. So I highly recommend you guys to attend the tutorial tomorrow. Yeah. Okay. Uh, For the team creation, the test data is already released. Check your email. The test data is already released today, so you could start making submissions. But remember, start making your submissions only after you have created the team. So if we see that you have made a submission without the team, like you might get a 0. So make sure you have formed the team of 3 and then try trial submission. Okay, so it is just 2 submissions per team. So as a team, if let's say 2 of your teammates already submitted today, then you cannot submit. So you have to coordinate with your team members. Okay, I think this information, Aryan, is given in the problem statement already. I think you can pick 2 best models in the end or something. Oh, registration in the Google. Oh, okay. For Google registration, please do only 1 per team. Oh, did you guys do more than 1 per team? Then I need to deduplicate your entries. No, I don't see any duplicates in the entries, but we have only 33 teams signed up. So please finish your signing up by tomorrow. I'm not sure if you receive any confirmation from Kaggle, but when you go to your team page, you should be able to see your team members. Yeah, that's what I'm saying, Masood. Like, so I don't think I'm not sure if you're going to get a confirmation from Kaggle for the team formation. So like, once you log into your Kaggle for the competition, like you should be able to have a team tab. And if you click the team tab, if you have already connected with 2 other team members, it will show that you are a team of 3. The scoreboard is accuracy. And I think this information is already given in the problem statement. Please read the problem statement very carefully. Like if you don't follow the rules, you get 0. So it's a very simple decision. Okay, someone says you will get an email from Kaggle when the merge is done. I'm not sure, like it might be true. Okay, any other questions? Okay, if there are no more questions, I think we can question about assignment 3. Yeah, what's your question? Okay, maybe I'll let the students mute themselves. You can unmute yourself and speak. Chana,
Yes.
if you want. Thank you.
Yes. Hello.
Yeah.
Yeah, I had a question concerning the score of between the test set and the validation set.
Okay.
So I have basically, when I use grid search CV for any classifier, I'm always getting the same score or about the same score for the training and the validation set. And I was wondering if that's normal, or should I expect a different score for them?
That's not normal, but I don't know this specific case. Are you sure that you are giving the right training and validation set? Are you accidentally giving the same set for both training and validation?
Well, when I use grid search, I basically merge the validation and training sets together and fit using the merged result. And I specify the split using a list of zeros and -1. So 0 for test and -1 for validation.
Okay, I am not sure how this grid search code works. So maybe I should talk to one of the TAs in the office hours.
Okay. I think tomorrow there's an office hour. All right. Thank you.
Okay. 5A, yeah. So I still haven't processed the emails from A1. I will do it. Sorry for the delay. I think there are only like 2 or 3 emails which are not processed. I will do it. But Charan, what about A2? Like all the regradings are done?
No, Abdul's are pending. So yeah, I'll ask him to do by the end of this week.
Okay, as soon as possible. Okay, so I think we will stop here.
Hi.
Yeah.
I have a question about Jupyter Notebook. Since each time I close the software, all the variables are erased. I don't know if you know why it is happening this, since I need to run each time all the cells, you know?
Oh, well, that's normal, right? Like, so if you're closing the notebook, then you need, it will have caches of just the output, not the variables, some state variables.
Oh, but for example, if you want to use a function that it's set in a previous cell,
You need to recompute everything if you're closing the notebook and opening it again.
oh, really? Okay, okay. I thought you could use.
Okay, when you open it again, you might see the output of the cell, but that's because only the output is cached,
Okay.
not the state
Okay.
variables.
Okay, okay. So you need to run everything another time.
Yes.
Then. Okay. Thank you.
Okay.
Yeah, and if you want to see the cached output, it is suggested to always save and pin your revision. The latest one.
Okay.
What? Sorry.
So it's always better to save and pin your revision, your final or latest revision.
So it seems there is an option to pin your versions. Okay, I didn't know that.
And
Yeah.
how you can do that?
Just go to the save option. There's file option. There is an option you can find it easily.
Okay. And you can save variables and also everything like functions you create.
No. Those things will not be saved. So those things can never be saved.
Okay.
Only
Okay. So can you repeat what is saved exactly?
no, sometimes the output also might be lost, when you close it or when you rerun it or something like that. So it's always better to save and pin your latest revision after you submit.
Okay.
Okay, as you're not submitting an online copy, I think it should be fine. But yeah, if you're submitting, Google Colab link or something, yeah, that is needed. But otherwise, you don't need that.
Okay. Thank you.
Okay. Anything else before we stop?
There's a question saying I'm still waiting for grade for us.
No, I have answered it. I have answered it. Okay, so I will stop the recording.